and I can do the equivalent circuit that I mentioned in the beginning, right? So what would this look like? This would look like so. There are all these resistances, but there's an additional resistance that leaves here, and it competes with the convective heat transfer, and goes like so. And this would be, our H equivalent right here. Now, to go from this system back into a simplified system, we know all we need to do is get an equivalent for these two fellows here. And to do that, all we do is know R equivalent for a resistance in parallel is just going to be 1 over the R3 plus 1 over the resistance for radiation, I guess. Let's put it this way. Minus 1. Yep, so as simple as that. Well, we have everything we need. This is 1 over, what was it? 0.20 something, 0.27, 0.27. And this guy here, we can do it here, or we can do it here in the corner. It doesn't matter, because we know the resistance for the radiation, the equivalent one for radiation is just going to be 1 over the one we just found times the outer area. And this I got to be, well, 0.28. 0.28. And then the equivalent to the minus 1. And the equivalent of this whole thing is about 0.14. So this math, is that right? 0.14, 0.29. Oh, excuse me, this is 0.29. Let me just check. There's no mistakes here. Yeah, there you go, 0.29. My bad. So R3 is 0.29. And this is 0.28. This gave me 0.14 as the equivalent resistance. Okay, and what does that mean? Well, it means that if I were to have a, where's my thing? Here it is. A system that would be the 25, the convective there, the conductive there, and then here instead of having R3, now we have an equivalent resistance for the parallel system, right? So we're combining both the convective and the radiation disguised as a convective in one, and this is going to give me a new sum of R's. And this sum of R's is going to be the 0.14 plus the 0.016 was it, and then the 0.01011, and that gives me 0.25, 622, 0.25, 6.2 is fine. Now we go again, because now we're going to find everything differently, right? Why is that changing? Because now we know Q will change because Q is dependent on delta T divided by the sum of R's, and in this case my delta T is still the same, still 15, the 25 minus the 10, but now my sum of R's changed, and it changed to 25.62 that I just found, and this is going to be 58.55. Again, let's not forget that we consume everything per meter length, so this would be per meter. And note how this changed, right? We originally found this to be, where is it, 37, and now we just found it to be 58.55. We're going to do this whole thing once again, do it a bit faster now, and then we need to check if it's going to change yet once again. When it stops changing, and hopefully it should stop changing in only a couple of iterations because this is an exam after all, we would have found our final, our convergence value, which is theoretically the correct value for this guy here. Right, so let me once again calculate T out. To do that, I'm going to do the same thing again. So the delta T, right, delta T will be my UQ, so the 58.55 times the two resistances, and these did not change. So this is R1 plus R2. These did not change whatsoever. This gave me 6.8 Celsius or Kelvin. So therefore, my T out will just be my 25 minus my 6.8, which gave me 18.2 degrees Celsius. Okay, so this is our new values. This is for Q and this is for T outside. What do we need to do? Well, rinse and repeat. Let me go ahead and grab this. And we're going to do it once more here in the corner. That's good. Okay, so once again, we're going to do this. Now, what changed from before to now? Well, this is not 20.7 anymore. This is now 18.2. 18.2, which gives me a new Q. In this case, it gave me a Q of 28.9, 28.9 for radiation. If I now pretend this is convection, then this becomes 28.9. This is not, I should keep it in red, what I'm changing, 28.9, this is new. And now this changes as well, because now this is 18.2. And this gives me a value of 5.1 approximately. Okay, and now with 5.1. With the 5.1, once again, I'm going to do the whole thing. So what is the, if I now flip this, and if I want interested in the R for the radiation, just be 1 over external area and the 5.1 that I found. This turns out to be about 0.28. And this is where we start to smile, because if this is 0.28, once again, kelvins per watts, this is 0.28, come on, 0.28 Kelvin per watt, then that means that our resistance for the radiation barely changed. Now, when we change these values here, right, and it's 0.28, and then it means that instead of having, instead of having, no, I would have a 0.28 again here, so it'll give me 0.14 again, which then that means that the whole thing is going to, converge to the same value. And that means that whatever we found before is correct. So these values here, where are they? These values here, that is this guy here is actually our answer, or close to our answer. And this guy here is also close to our answer. Okay. Now, if you're doing this on an exam, you probably won't have time to check. I did check to see if it would continue changing, because if you don't approximate this, then you're going to get a slightly different value. This is going to be slightly different too. And I did continue doing it, and then the next iteration I got 57.78, so very close to the previous one, and temperature I got 18.3, so very close indeed. And then if you're not satisfied with this, I actually did an Excel sheet, and I'll show you the Excel sheet. What I did here is the things on the top are kept constant, or constants, and then on the bottom I'm calculating Q at every iteration, I'm calculating the temperature out at every iteration, calculating the new radiation emission, the new H equivalent, the new resistance for radiation, the new equivalent for the parallel system, and the new sum of resistances. And you can see on the very right, where you have the yellow values there, that indeed the Q converges to 57.8. Okay, and we stopped in 58.55, so that will be 100% okay, acceptable. And our temperature converges to 291.3, which is the 18.3 I told you guys about in Celsius, obviously. Okay, so this is one way to do it. Remember, the assumption where the whole thing came from was where is it? Assuming a simple system without radiation. And after we found the first TO, or T outside, then we calculated radiation, we saw how things changed, and then we did some iterations on that. You could have made other assumptions. I might do a separate video in which we do it differently. Hope this helped you out. If you have any questions, as per usual, just leave them down below. If not, we'll talk soon. Okay, so I thought about it, and I think it's not worth doing a whole video just on the second way. It's actually easier for me to show you in the same video. So this is what I thought. To do this way, I'm going to do, the assumptions, the underlying assumptions are all the same, except for the assumption of this outer temperature just here, right? What we call TO in the previous one. And then what I did here is, instead of doing, the simple thing here, ignoring radiation, what I did is I just guessed this temperature. Okay? And the guess that I took, because I know it has to fall between 10 and 25, I know that for sure. I just guessed, the value right in between. Just took the simple mean. That's the 25 plus 10 divided by 2, 17.5, and that was, my initial assumption. So instead of doing the calculations, I just jumped straight into it. Because with that, what it allows me to do is now calculate, my radiation, Q for radiation. And then note that now I'm calculating everything in heat flux, because, we saw that the outer area just keeps popping up and out, in and out of our equation. So just leave it in heat flux so we don't have to worry about the area. And then first, straight off the bat, I got 40.12 as my radiation flux, heat flux. Then I converted this into the equivalent H, and I got my 5.35 as the equivalent H, which give me a resistance, equivalent resistance for radiation of 0.27. Okay, so I start already with a, the first circuit that I draw already has the parallel system with the radiation and the convection competing. Well, this converges exactly to the same value as before, but it converges faster because we start, our first guess is already closer to the final answer. In an exam setting, this is just, your lucky guess. You can do whatever is reasonable. So in this case, if you were to do it this way, what happens is, the process of doing it is the same. You just start from different points. So then you calculate the equivalent resistance for the parallel system. You calculate the resistances for each of the things. You sum them up. You get a sum of R's of 0.25, and you calculate the first Q that you've ever calculated is 59.1. So you see it's already, way closer to the final answer that we got, the 58 point something, 59 point something, than the previous method. Then we just do it. We have to do it more times because we want to be sure we're getting close, right? So we do the whole thing. So we recalculate the T. Now considering the new Q that we found, this is going to give us 18.1. So you already see we're closer. We went from 17.5 to 18.1. Calculate radiation once again, substitute the 18.1 where we had the 17.5 before, get a heat flux of 43, convert that into equivalent convection, calculate radiation resistance. Note that this is 0.27, just the same as the previous one I calculated. Where is it? The 0.27, where are you? Here you go. Just the same as the 0.27, so that means that from this point on, nothing's going to change. I'm going to keep getting 8.13 something. I'm going to keep getting my, what's the Q? I'm going to keep getting Q as 59.1. Okay, so with only one iteration, or actually two iterations, you can see already this is working.